Remarkably, tests are already underway here on the Canary Islands off the coast of Africa.
We do the experiments here on the Canary Islands because you have two observatories, and after all it's a nice environment.
Anton Zeilinger is a long way from teleporting himself or any other human. But he is trying to use quantum entanglement to teleport tiny individual particles, in this case photons, particles of light.
Nanometers, it says.
He starts by generating a pair of entangled photons in a lab on the island of La Palma. One entangled photon stays on La Palma, while the other is sent by laser to the island of Tenerife, 89 miles away. Now Zeilinger brings in a third photon, the one he wants to teleport, and has it interact with the entangled photon on La Palma. The team studies the interaction, comparing the quantum states of the two particles. And here's the amazing part. Because of spooky action, the team's able to use that comparison to transform the entangled photon on the distant island into an identical copy of that third photon. It's as if the third photon has teleported across the sea without traversing the space between the islands.
Sort of extract the information carried by the original and make a new original there.
Using this technique, Zeilinger has successfully teleported dozens of particles. But could this go even further? Since we're made of particles, could this process make human teleportation possible one day?
Welcome to New York City.
Let's say I want to get to Paris for a quick lunch. Well, in theory, entanglement might someday make that possible. Here's what I'd need. A chamber of particles here in New York that's entangled with another chamber of particles in Paris.
Right this way, Mr. Green.
I would step into a pod that acts sort of like a scanner or a fax machine. While the device scans the huge number of particles in my body, more particles than there are stars in the observable universe, it's jointly scanning the particles in the other chamber, and it creates a list that compares the quantum state of the two sets of particles. And here's where entanglement comes in. Because of spooky action at a distance, that list also reveals how the original state of my particles is related to the state of the particles in Paris. Next, the operator sends that list to Paris. There, they use the data to reconstruct the exact quantum state of every single one of my particles. And a new me materializes. It's not that the particles traveled from New York to Paris. It's that entanglement allows my quantum state to be extracted in New York and reconstituted in Paris, down to the last particle.
Bonjour, Monsieur Green.
Hi there. So, here I am in Paris, an exact replica of myself. And I'd better be, because measuring the quantum state of all my particles in New York has destroyed the original me.
It is absolutely required in the quantum teleportation protocol that the thing that is teleported is destroyed in the process. And, you know, that does make you a little anxious. I guess you would just end up being a lump of neutrons, protons, and electrons. You wouldn't look too good.
Now, we are a long way from human teleportation today, but the possibility raises a question. Is the Brian Greene who arrives in Paris really me? Well, there should be no difference between the old me in New York and the new me here in Paris. And the reason is that, according to quantum mechanics, it's not the physical particles that make me me. It's the information those particles contain. And that information has been teleported exactly for all the trillions of particles that make up my body.
It is a very deep philosophical question whether what arrives at the receiving station is the original or not. My position is that by original we mean something which has all the properties of the original.
New York City.
And if this is the case, then it is the original.
I wouldn't step into that machine.
Whether or not human teleportation ever becomes a reality, the fuzzy uncertainty of quantum mechanics has all sorts of other potential applications. Here at MIT, Seth Lloyd is one of many researchers trying to harness quantum mechanics in powerful new ways.
Quantum mechanics is weird. That's just the way it is. So, you know, life is dealing us weird lemons. Can we make some weird lemonade from this?
Lloyd's weird lemonade comes in the form of a quantum computer.
These are the guts of a quantum computer.
This gold and brass contraption might not look anything like your familiar laptop, but at its heart, it speaks the same language, binary code, a computer language spelled out in zeros and ones, called bits.
So the smallest chunk of information is a bit. And what a computer does is simply busts up the information to the smallest chunks and then flips them really, really, really rapidly.
This quantum computer speaks in bits, but unlike a conventional bit, which at any moment can be either 0 or 1, a quantum bit is much more flexible.
You know, something here can be a bit. Here is 0, there is 1. That's a bit of information. So if you can have something that's here and there at the same time, then you have a quantum bit or qubit.
Just as an electron can be a fuzzy mixture of spinning clockwise and counterclockwise, a quantum bit can be a fuzzy mixture of being a 0 and a 1. And so a qubit can multitask.
Then it means you can do computations in ways that our classical brains could not have dreamed of.
In theory, quantum bits could be made from anything that acts in a quantum way, like an electron or an atom. The qubits at the heart of this computer are tiny superconducting circuits built with nanotechnology that can run in two directions at once. Since quantum bits are so good at multitasking, if we can figure out how to get qubits to work together to solve problems, our computing power could explode exponentially. To get a feel for why a quantum computer would be so powerful, imagine being trapped in the middle of a hedge maze. What you'd want is to find the way out as fast as possible. The problem is there are so many options. And I just have to try them out, one at a time. That means I'm going to hit lots of dead ends, go down lots of blind alleys, and make lots of wrong turns before I finally get lucky and find the exit. And that's pretty much how today's computers solve problems. Though they do it very quickly, they only carry out one task at a time, just like I can only investigate one path at a time in the maze. But if I could try all the possibilities at once, it would be a different story. And that's kind of how quantum computing works. Since particles can, in a sense, be in many places at once, the computer could investigate a huge number of paths or solutions at the same time and find the correct one in a snap. Now, a maze like this only has a limited number of routes to explore, so a conventional computer could find the way out pretty quickly. But imagine a problem with millions or billions of variables, like predicting the weather far in advance. We might be able to forecast natural disasters like earthquakes or tornadoes. Solving that kind of problem right now would be impossible because it would take a ridiculously huge computer. But a quantum computer could get the job done with just a few hundred atoms. And so the brain of that computer, it would be smaller than a grain of sand. There's no doubt we're getting better and better at harnessing the power of the quantum world. And who knows where that could take us. But we can't forget that at the heart of this theory, which has given us so much, there is still a gaping hole. All the weirdness down at the quantum level, at the scale of atoms and particles, where does the weirdness go? Why can things in the quantum world hover in a state of uncertainty, seemingly being partly here and partly there, with so many possibilities, while you and I, who after all are made of atoms and particles, seem to always be stuck in a single, definite state? We are always either here or there. Niels Bohr offered no real explanation for why all the weird fuzziness of the quantum world seems to vanish as things increase in size. As powerful and accurate as quantum mechanics has proven to be, scientists are still struggling to figure this out. Some believe that there's some detail missing in the equations of quantum mechanics. And so, even though there are multiple possibilities in the tiny world, the missing details would adjust the numbers on our way up from atoms to objects in the big world so that it would become clear that all but one of those possibilities disappear, resulting in a single certain outcome.